ED27, and this will be a short presentation explaining the designing process for a repeatable vehicle.
As a group, we began to discuss all the possible problems with the car and its environment. Following this, we began to narrow down what would be the main problems we would have to solve. This then started the phase in which we were brainstorming solutions to our problems, then decided on the best solution and developed those ideas.
The initial idea we thought of was to use springs. It works by having two springs on the front of our car. Those springs would have two purposes. The first purpose is to slow the car down, which we decided to keep on our final design. The second one was that it would create enough of a reaction force so that when it hits the wall, it will rebound and land at the bullseye. However, the plan was abandoned because the system is too hard to control. This is because if the springs produce too much force, then large oscillations may occur and cause the vehicle to move unpredictably.
The idea we came up with next was to have a bearing that rotates and use it to ensure that when it returns, because of the stoppers attached to them, the bearings cannot pass its initial position. The problem to this system is that the cost will exceed our budget, and it is hard to assemble this in reality.
To drive the vehicle, we chose our RE140 motor. Our criteria when picking the motor was to have a low cost and a good value for our RPM. However, we didn't want our RPM to be too high because we didn't want to mess up our gear ratio. The requirement for the voltage of the motor should have also been low to reduce the power supply. Now, our RE140 was chosen because it has a relatively low RPM of 8,200. It only requires 1.5 volts, which means only a single AA battery was needed for it.
In order to drive the whole system, we choose 5 80th gears and 5 40th gears. Each of the 40th gear will have an 80th one attached to them, except the top one connecting the gear rack. So that we can make sure that overall gear ratio from the motor to the back wheel is 1 to 125, and the same as the gear ratio between the wheels and the rack. We use the rack and pinion system in order to stop a vehicle at the initial position. The rack will go in opposite direction as the car moves. When the car returns to the datum position, the stopper at the back of the rack will go to stick the rack and the gear together and stop the rack to move forward, which will also stop the motion of the vehicle.
As we're using a simple DC motor, reversing the current through the motor respectively changes the direction of the motor rotation. Thus, we use a two-way switch with two wiring systems which have the current coming from the either way. When we had that figured out, we had to find a way out to flip the switch. This is when we took advantage of our rack and pinion design. We calculated that the rack would go back 80.4 millimeters when our car hits the wall. So we put our switch 80.4 millimeters behind our rack so it can be triggered by the rack when it hits the wall.
Even though we were confident in our calculations, we wanted to implement the motion that we had planned into our CAD designs. This is why we set up motion links in every gear, including the motor and the rack. This helped us visualize the motion of our car and helped us explain our idea easier to teammates.
There are three main talking points we had on choosing the materials. The main material we had to be cheap, easy to customize, and strong. We found the perfect balance at Ashwood. It was relatively cheap, strong enough to make the gears from, and easy to customize with a saw. The only place where we thought the strength was more important than the cost is the axle. We use an aluminum rod for the axle as it is stronger than wood but cheaper than steel.
The total cost totaled to £25.28, excluding the wires. Breaking down the costs, we need £8.53 for the Ashwood, £2.39 for the aluminum rods each, £1.19 for our motor, £3.79 for our switch, and finally £4.79 for our batteries.